Hello everyone, my name is Yan Huang. I'm currently a system software engineer at NVIDIA. I received my PhD degree in electrical engineering from Virginia Tech in December 2020, and my PhD advisor is Professor Tom Ho. The paper I'm presenting today is titled A Deep Learning-Based Link Adaptation Design for eMBB and URLLC Multiplexing in 5G NR. This paper was co-authored with Professor Tom Ho and Professor Wenjing Lo. 5G NR is the new radio access technology developed by 3GPP for the 5th generation mobile networks. The service types of 5G NR can be classified into 3 major categories, including the enhanced mobile broadband, eMBB, the massive machine type communications, MMTC, and the ultra-reliable and low-latency communications, URLLC. eMBB focuses on supporting the ever-increasing end-user data rate and the total system throughput. MMTC targets at providing massive connectivities for the low-power IoT devices, while URLLC aims to achieve a 1 millisecond level end-to-end latency for delay-sensitive applications. In 5G NR, a major technical challenge is to dynamically multiplex different service types over the same frequency spectrum. In this paper, we focus on the co-channel multiplexing of eMBB and URLLC. Imagine a 5G cell that serves a number of eMBB and URLLC and users on the same channel. According to the 5G standards, eMBB data traffic is transmitted in regular time slots. The duration of a time slot depends on the OFDM numerology employed for the cell. For example, the slot duration is 1 millisecond under numerology 0. In contrast, in order to minimize the transmission latency, URLLC data traffic is transmitted in mini-slots, where a mini-slot can be as short as 2 OFDM symbols. For example, a 2-symbol mini-slot is merely 71 microseconds under numerology 0. Then a key question is, how can we ultimately arrange the slot-based eMBB transmissions and the mini-slot-based URLLC data traffic on the same channel? A promising approach to the dynamic multiplexing of eMBB and URLLC data traffic is the preemptive puncturing mechanism. Specifically, an unarrived URLLC packet will be transmitted immediately in the next available mini-slot. The frequency resources required for this transmission are obtained by preempting the ongoing eMBB transmissions on the channel. For example, the figure in this slide shows the resource allocation for 3 eMBB users on the channel. In each TTI, when a URLLC packet is transmitted, a chunk of contiguous frequency resources are directly punctured from the channel, which are represented by a yellow bar, regardless of the ongoing eMBB transmissions. Although this preemptive puncturing scheme can effectively minimize the latency of URLLC, the downside is that the eMBB performance will be adversely impacted. In particular, the LDPC decoding of unreceived eMBB code block may be failed due to the puncturing from URLLC. More formally, preemptive puncturing will result in the eMBB performance loss in terms of both data throughput and link reliability. 5G standards define 29 levels of modulation and coding schemes, or MCS. Each eMBB transmission is assigned with one of the 29 MCS levels to match the channel quality on its allocated resources. Link level simulation results show that under URLLC puncturing, the block error rate, or BLER, of each MCS increases, which corresponds to a worse link reliability. On the other hand, the achieved data throughput under each MCS decreases due to the puncturing. However, in our study, we found that a smart MCS selection for eMBB can effectively mitigate such adverse impact from preemptive puncturing on eMBB. We present link-level simulation results in the following two figures to showcase such effect. Consider a specific communication link between the base station and an eMBB user. At the beginning, this eMBB link was configured with MCS level 10. We turned on the URLLC data traffic and preemptive puncturing at TTI 5000. Obviously, both of the BLER and throughput performance for the eMBB link got severely impacted if MCS level 10 is still being used after TTI 5000. But if we switch to a lower MCS level, say MCS 6 for this eMBB link, such adverse impact is largely mitigated. So the idea is simple. When preemptive puncturing is present, we should always use lower MCS levels for eMBB transmissions compared to the case where we only have eMBB transmissions on the channel. Now the question becomes, how can we find the best MCS? That is the problem we address in this paper. Specifically, we aim to find the most suitable MCS for each eMBB transmission under URLLC preemptive puncturing, such that the spectral efficiency of eMBB is maximized, while a given target BLER is met. In practice, a typical target BLER for eMBB services is 10%, meaning that the LDPC decoding failure probability of each eMBB transmission should not exceed 10%. The biggest challenge in solving this problem is that it is mathematically intractable. Simply put, we don't have an analytical model to determine the BLER of each MCS level under preemptive puncturing. It is well known that LDPC decoding performance in terms of BLER is very difficult to model in closed form. As in the examples here, when a URLLC transmission is present and punctured an eMBB transmission, we just don't know what exactly the BLER will be, no matter which MCS is used for the eMBB transmission. As a result, we cannot use conventional optimization approaches to solve this problem. In addition, in 5G NR, we have the real-time requirement on 125 microsecond timescale, which is the shortest time slot duration under numerology 3. An MCS selection method must have an execution time smaller than this timing requirement to be useful in practice. In order to solve this problem and address the challenge of having no analytical model, we designed a deep learning-based link adaptation method for the eMBB MCS selection under URLLC puncturing. The key idea is to employ a deep neural network to learn and predict the BLER of each MCS level under preemptive puncturing. With such predicted BLERs, we can find the most efficient MCS for eMBB while meeting the target BLER requirement. In particular, our design consists of 3 stages that are executed in serial, including stage 1, which translates the original high-dimensional information of eMBB into a low-dimensional representation, and stage 2, which is a neural network that predicts the BLER of each MCS level, and stage 3, which selects the best MCS to be used for the eMBB transmission based on both the BLER predictions and the recent decoding performance of each eMBB user. Next, I will talk about more details for each of the 3 stages. First, before stage 1, we have the complete information about an eMBB transmission. It includes the channel conditions across both frequency and time on the resources allocated to the eMBB transmission, as well as the approximate URLLC puncturing on its resource allocation. If we directly use this high-dimensional eMBB description, we will have to employ a very complex layer structure for the neural network in stage 2, which would cause a high execution time that violates the real-time requirement in 5G NR. So we propose a method to convert the original eMBB description into a low-dimensional representation. Our method was designed with an objective of minimizing the information loss caused by such conversion. Stage 2 consists of a deep neural network that takes as input the low-dimensional representation from stage 1 and outputs the predicted value of 1 minus BLER for each of the 29 MCS levels. These 1 minus BLER predictions will be used as a basis for the subsequent MCS selection. The neural network in stage 2 should be properly trained in order to meet the goal of BLER prediction. But a challenge in this training is that it is practically very difficult to obtain a data set with actual BLER values from a large number of eMBB transmissions. To address this challenge, we propose to train the neural network with a learning objective that only involves the binary ACK and NACK decoding results of eMBB transmissions. With this learning approach, there is no need for determining the BLERs, which are very hard to obtain in practice. The learning phase consists of 2 steps. The first step is to collect a large number of eMBB transmission samples with randomly selected MCS levels and actual ACK or NACK decoding results. Then the second step is to perform stochastic gradient descent to train a neural network. Finally, stage 3 selects the best MCS level to be used for the eMBB transmission. An issue needs to be addressed by stage 3 is that the BLER predictions from stage 2 may contain certain errors. Such prediction errors are inevitable in practice since we cannot traverse all the possible eMBB transmission samples when training the neural network. To ensure the target BLER can be met in spite of such prediction errors, for stage 3, we propose to exploit the recent decoding history of each eMBB user. As an example, assume the target BLER is 10%. If the empirical BLER is far below the target, which implies that the neural network underestimated the 1 minus BLER values, we add a small positive calibration to the predictions. On the other hand, if the empirical BLER exceeds the 10% target, we add a small negative calibration to the neural network's output predictions. With such predictions in stage 3, although the BLER may validate the target for some TTIs, it will be brought back to the target very quickly. In order to meet the real-time requirement in 5G, we implement our solution using an off-the-shelf NVIDIA V100 GPU. This GPU-based implementation enables the concurrent processing of all eMBB transmissions scheduled for a TTI, such that the execution time of processing multiple eMBB transmissions is equivalent to that of a single eMBB transmission. We run extensive link-level simulations to evaluate the performance of our solution. For performance benchmarking, we also implemented the exponential effective SNR mapping, the EESM method. EESM is a popular link adaptation algorithm for OFDM systems such as 4G LTE. The test scenario has 10 eMBB users in the cell. To eliminate the impact of using a particular scheduler, we employed random resource allocation for the 10 eMBB users. The URLLC traffic load is 2 packets per TTI. The following two figures compare the BLER performance of our solution and EISM. Clearly, our solution can stably maintain the target BLER of 10% for all users, while EISM results in a large violation of target BLER. In terms of throughput, our solution is able to achieve a comparable performance with EISM. Note that our solution works under the strict constraints of maintaining the target BLER, while EISM is free of such constraint and only targets at maximizing the spectral efficiency. To evaluate the execution time against the 5G real-time requirement, we considered a wider range for the number of eMBB transmissions per TTI. The results confirmed that for a maximum of 50 eMBB transmissions per TTI, our GPU-based implementation can successfully meet the timing requirement of 125 microseconds under 5G numerology 3. That is all I present today. Thank you.